and then other student will come in later. So we are still at the module 5 right now, and we are at the assignable cost analysis topic, right? Last time we really talked about the fishbone diagram and the 5 why techniques, and today we need to move on to the third technique. So it's about the Pareto diagram, and I would like to share with you the slides that we need to work on. So it's on slide 64, the module 5, right? Okay, so the big topic is assignable causes, and we talk about the third technique to deal or to investigate for the causes of variation, right? In this case, we have a look at the online retailer, and as a service provider, right? They are concerned about the number of transaction errors, and of course, they want to reduce the number of transaction errors. So to do that, they investigate for the causes of the errors, right? They collect the data, and here is what they have. So the browser error is one of the problems. Order number out of sequence, product shipped but credit card not billed, and other entry mistakes, and then product shipped to the billing address, and brown model shipped, right? So these are all of the possible causes of the transaction errors. And the managers will need to look at these data, draw the Pareto chart down here, and we'll think about what to do with it, okay? So let me go to the whiteboard, and I would like to show you the details, more details of this example. So we are still at module 5 about quality management. Right. And the big topic that we are at right now is assignable cost analysis. If you can recall, this is the third main activities in SBC, right? Okay, so we observe that there's a special variation, and we try to find the cause of the causes of that special variation, right? Last time we already talked about the cause and effect diagram. That's one way to investigate for the causes. Right. We call this as a fishbone diagram because it looks like it, right? And you would need you would have a chance to practice with this in project part 5. Right. So last time we talked about this, and then the second technique is a 5 why techniques. Okay, and I encourage you to read more about that toilet example, right? And then the third technique that we learned today is called the Pareto diagram. So this is the E. Taylor example. e-tailer is just like e-commerce and retailer combined together, right? So this one is module 6. I'm sorry, module 5 and slide 64. And what we're doing with this example is very similar to question 21 in our homework 3, part 2, right? So I hope that you see that this is a short and easy question in that homework 3, part 2. All right, so to do this, we're gonna draw the table of the following. In the first column, we're gonna list out the causes of the transaction errors, right? So here are the other causes. The first one is browser error. Because of some technical errors, the customer might see different things. They buy different things instead of the things that they want to buy, right? So something like that will cause the transaction errors. A second example here is the order number out of sequence. Okay, here I try to make it short, so I just write out it as out of sequence. When the order of the transaction or the order number out of sequence, some customers, right, might have to wait much longer than the regular wait time. For example, if you go to Amazon, they mixed up with the order in some way. You will receive your merchandise like 2 weeks later, right? And you're not happy with it, you complain with them, right? Then that's one error right there. Not to mention because of the mixed up of the order numbers, right? Then they might send different things to different customers, and that would be very bad. All right. So the third possible cause here is product shipped, but the credit card's not billed. Obviously, this is one error because we do not receive the revenue for selling a product. We just lose the product for nothing. Right? The fourth cause of error here is order entry mistakes. Right? Some of the communication might be by phone, or for some reason we enter the information wrong, right? And then the transaction will be an error. The fifth cause here is product shipped to the billing address. Why is that an error? It sounds like normal, right? But in the reality, for example, when you go to Amazon.com and you want to buy a gift for someone else, right? Then the item needs to be shipped to the recipient, not you as a buyer. But they ship to you anyway. Then you have to take that and then ship that to the recipient, and that's a double cost by that, right? It's not good. You even like call the e-tailer to complain about it, and then they might refund you the cost to send to the intended recipient. All right, so 1, 2, 3, 4, 5, and the sixth one is the wrong model set. Right? Sometimes we do experience this firsthand. We buy something, this color, that model, that feature, but they send us something else, right? So definitely that's another very possible cause of errors in the online operations, right? All right, so we resolve another row at the end here. for the total. Okay, so that's the first column. The second column is the frequency of how many times each of these causes happens, right? So the frequency are our data. The browser errors happen 43 times. The second order number out of sequence happens 29 times. Caught not billed 16 times. Entry mistakes 11 times. Shifted the billing address is 8 times. And wrong models happens 3 times. So these are called the frequencies, just the number of times that these or the other thing happens, right? Okay, so of course, it's easy to add all of these up. We talk about a total of 110 errors here. The third column tells us about the cumulative percentage. I'm sorry, the percentage. So if we look at that number 43, we do not really see the big picture, right? We only know that, okay, the browser errors happen 43 times. But we do not have the knowledge of how big it is among all of the problems, right? So that's why in the third column, we try to make more sense of our data by calculating the proportion. So 43 out of 110 is what? We take 43 divided by 110. Then we have 0.39 or 39%, right? So that's the first percentage. The second one, by the same token, we're gonna do 29 divided by 110. Then we have 26%. On and on, we will do the same for the other causes. The third one would be 15. The fourth one would be 0.10. The shift to billing will be 0.07 or 7%, and the wrong model will be 0.03 or 3%. And of course, if we add all of these up, we have 100% of the problems or 1.0, right? Okay, so that's the third column. And now let's talk about the fourth column. The fourth column might be new to some of you. It is about cumulative percentage. Right? What is that? It means the following. After we make the first step, we deal with the first problem. How much of the problems that we have covered, right? So that's the first step. So if we take the second step and cover the first and the second causes here, then how much of the problems that we have covered, right? So that's a cumulative sense. It means that we have to add things along the way, right? And here is how we would do it. The browser error is the first step. Oh, by the way, I forgot to mention one thing. This data is already sorted, right? From the highest value to the lowest value. And we would call that as a Pareto sort, the name of the person who used this sort first. That's Pareto sort. So that we can see the highest value first and then the lowest value last, right? All right, so let's go to the cumulative percentage column. What we do is the following. When we make the first step, we cover 39% of the problem, right? And after the first step, we take the second step. then we would cover the first plus the second. And then we have 65% of the problem. And when we calculate the third, when we take the third step, we would cover 1, 2, 3, right? So by definition, we would add the three numbers together. But in this case, we can do the following trick. We just take the previously accumulated value and add with the new step, right? So we would take 0.65 plus 0.15, then we have 0.80 or 80% of the products. And then we take the fourth step, then we cover 0.8 plus 0.10 equals 0.9 or 90% of the problem, right? Okay, and then if we try it harder, make the fifth step, then we will cover 97% of the problems. And finally, if we go all the way to the last step, then we cover 0.97 plus 0.03 will be exactly 1.0, which also means that we cover all problems, right? 100% of the problems. Okay, so that's accumulation right there. Right? We work more and more, go further and further, then we would like to see how much we have covered along the way. In this table, we should do the total down here because we already did the totals along the way, right? We don't want to double count it, so we should not do the total at the end of the column. All right. So it's very similar to question 21 in our homework 3. You would draw a table like this and go through all of the manual calculation like this. All right. So next, what we want to do is we would like to draw a chart, a diagram, right, to reflect upon the numbers that we have here. So it will look like the following. So this is called the Pareto diagram, right? It looks like the following. So we lay out the causes horizontally. We use one vertical axis for the number of errors. And we want to show the cumulative percentage at the same time. So in our graph, we have another scale like this, right? And this second scale is a cumulative percentage. So we would draw the Pareto diagram like exactly what we see in the table. So the first column has to be the tallest. And then the next column, the third one, the fourth, fifth, and sixth, right? Okay, so this is called the Pareto diagram. But of course, because we are interested in the cumulative percentage, by the way, after we sort the things right, then down here we have the cause number 1, cause 2, 3, 4, 5, and 6, right? And because we want to see the cumulative percentage, we would start from somewhere here, and then we add we accumulate the percentage along the way. So it might look like that, like that, like that, and finally it's like that. And at that point, we hit exactly 100%, right? We accumulate all the problem along the way. So this columns right here is a traditional Pareto diagram. And the part on the top, the part right here is called the percentage OGI. Possibly you have never seen this before. This time is the first time that you see it, the name. So the percentage OGI is just the accumulated values after we already sort the columns, right? The data. Okay, so we are done with this Pareto diagram. When you work on question 21 of the homework 3, beside the manual chart, you can also do that in Excel too. Right. So the last part of the question 21 asks you to redraw this graph in Excel. So the first time you manually draw it to learn the concepts, and the second time you do it that in Excel to learn the skills, right? We need both the concept and the skill, computer skill, or software skill. All right, so now we already done with the Pareto diagram. This Pareto diagram is just the visual of the table that we have earlier, right? So as a manager, we look at this chart, and now we see that there are 6 possible causes of errors. Then what errors that should we deal with first, right? We are always limited in terms of resources, time, money, and manpower. We cannot deal with all causes at the same time, right? So in this case, we see multiple causes. And it requires prioritization, right? So prioritization is about what to do, or it says the following: we would deal with the biggest problem first. So what does that mean by the biggest problems first, right? We look at the number 1, and then number 2, number 3, but it's a little bit subjective, right? Some manager would like to go 1, 2, 3. Some manager would like to go 1, 2, 3, 4. So it's a little bit kind of situation specific, because it depending on the resource availability, resource availability, right? So if we have, let's start with the first 3 biggest problems. We have covered 80% of all of the problems already, right? 80% is a big number. We drastically reduce the number of errors of our process. But then if you have extra manpower, which means workers, and then time and money, then you would go further to cause number 4, and then cause number 5, right? Things like that. So it depends on our resources. And again, the resources here are money, time, and manpower. Okay, so it's kind of situation specific, and it's a little bit subjective, right? On what you want to do. Okay, so that's the 3rd technique that we should learn to investigate for the causes of spatial variation, right? So with that, I would like to close that topic so that we can move on to the next big topic, right? In the next big topic, we talk about robust processing. So this is what? This is the 4th main activity of SBC. Right, there are four activities. We did the first one, the second, the third, and this is the fourth one, right? So what is a robust process? A robust process can maintain output quality even if there are changes in the input and the environmental variables, right? So in face of changes in the input and environmental variables. So that's what it means by being robust. So we can kind of isolate or mitigate the impact from the input and the environmental variables. All right. So there are three big groups of methods that would help us to do that. We only talk about these at the conceptual level here. So I will list out the list of three major groups of methods. The first group of methods is called over engineering, right? For example, nowadays, by the new building code, if you want to build a new house, maybe you are required to make the house stronger to withstand larger earthquakes, right? So how do we do that? We can do the crossbars, the tension bars going diagonally like this. If you go to the building 164 of the College of Business, right, you might see that. By the way, when I say that, some of you even have not been on campus yet. You don't even know where the building 164 is. But in the spring, if you go there, right, if you go to the first floor, you might see some big diagonal beam going like this, right? It is made of metal. It's a big piece of metal that go diagonally like this. That will help the building to maintain its integrity in case of there's a big earthquake. Okay, so that is called over engineering. Right? In that case, in that example, we talk about larger tolerance. A lot of houses have to be retrofitted with the diagonal beam so that it can withstand the earthquakes, right? So larger tolerance by having better materials and stronger structure. Right? Then the process, the building, things like that can tolerate more impact from the environment or from the inputs. As a consumer, sometimes we break this or break that, but if they build it in metals rather than in plastic, right? Or other things, and the process, the products can withstand more forces. So we all call that as larger tolerance. The second part of the over engineering here is redundancy. Do you know that when you fly an airplane, normally there are double systems. The flight computers are two of them, not just one, right? Even three. So that if one system goes down, they will have other system to kick in and back it up, and the airplane can fly normally, right? or the control surfaces can also be double too. One surface goes down and is damaged, then the other can still work. So we have redundancy so that we can deal with all of uh, the impact from the environment or from the input, right? So double systems. Okay, but of course it's more costly. Instead of building one thing, now you have to build two or three things, right? And it is costly to do the double system like that. So that's the first big group of method. The second big group of method is called mistake proofing. Right? Or poka yoki in Japanese. We learn a lot of Japanese word in this module or the next module because a lot of the things we learn from the Japanese car manufacturers. So mistake proofing means the following. We would design the process so that it can straighten itself out even if as a human we make errors, right? We are human, we make a lot of errors here and there, but then because the process is very robust, it can straighten itself out. Our error doesn't matter anymore, right? So let me give you some example about it. In the old days, when we newly got the computers in the 1980s, after a long day of typing a Word document, things like that, somebody closed the file without saving it. Think about it, it's so painful, right? But then over time, the engineers can quickly came up with a solution. When you close the file, they will ask for if you want to save the file before you close it, right? Then it's hard for us to lose the work. But you know what? Sometimes our computer crashes, right? Then we lose all the work. So to make the process more robust, they will do the auto save. Feature. So we type it after 1 minute, it saves one time, for example. Another 1 minute, it saves another time, right? So because of that, it's harder for us to lose our work, right? Or nowadays we go online, do a lot of things online. You type an email, and then suddenly your computer crashes. Then you just reboot your computer, log in your email again, and then you see the drop right there, and then you just continue because it's already saved. When you type it, it's already saved, right? So that's one example of the poker yogi. Another example here is just ask yourself why you have never overfilled your car, right? We use a boom like this to fill in the gas tank. Why don't we overfill it from time to time? Because the process is designed to be very robust. When you put the boom onto the car, it has to be airtight enough. And when you fill more gas in, the air pressure will build up. And then at some point, it is too much. The boom will cut itself off, right? So that we do not overfill our car. That's another robust design right there, right? Another example for you is the following. In the past, people forgot their ATM cards, debit card or credit card at the ATM because at that time, right, the card is inside. You take the money, and then you just walk away. You know what? I myself made that mistake several times, at least two. Okay, but nowadays we don't have that problem anymore because before you can complete your transaction, even before you can do anything, they ask you to pull the card out, right? And then you put your card out, you securely put it somewhere, in your wallet or purse, and then you just go on with the transaction, and then at the end you just walk away without forgetting the cards. Or when you check out at the grocery store, before they give you the receipt, you have to take the cards out. So it is really hard to forget the cards, right? So that process is very robust. Um, we take it for granted now, but it happens in the 2000 times, 2005 or something like that. People still forgot the cards at that point in time. But nowadays, after 15 years or so, it's so much more robust. The third group of methods here is called early warning. So in this case, right, we would use a lot of sensors to alert something imminent, right? Like the smoke detectors or something like that. It stands for the CO2. That's a clue that there's a fire going on, right? And then something will light up to alert us. Something will make sounds to alert the imminent danger, things like that, right? So, and then as a workers, we will shut this off and the other things, right? So that we do not have the accident or incidents. Okay, so if you look at the back of the McDonald's restaurant, if you look at the kitchen, right, you will see a lot of lights, of sounds. All of those are the alerts to the workers, right, so that they can stop cooking the food. Otherwise, the food will get burnt, right? And a lot of the time, we use automation. For example, we need to microwave this food for 4 minutes. On the label, they say that it has to be 4 minutes. Then, okay, so just go ahead and do the 4 minutes. And after 4 minutes, right, the microwave will shut itself down so that we do not overcook the food or we do not cause any burns, things like that. Okay, so those are the three popular big groups of methods that will help us to make the processes much more robust, right? More robust means that even if, as a worker, we make errors, but then the process can straighten itself out, and we will not have the quality incidents, right? So that's the final topic of the SBC, but that's also the final topic of the whole module 5 about quality management. So I would like to move on to the next module right away. Let me share that with you. So module 6 is about lean operation. Let me share that with you. So lean operations, and this module is mainly based on chapter 8 in our textbook. And here is an outline of the module 6, lean operation as an overview. And then we focus on two perspectives to identify the waste and eliminate the waste. And the final part of the whole module is about the toilet production system, right? Why toilet production system? Because lean is pioneered by Toyota, and a lot of the practices that we do today in manufacturing, in services, we learn it from Toyota, right? So that's why we take Toyota as a benchmark, as a role model uh, to improve our process. All right, so what is lean? The keyword lean is coined by Professor James Wimmick, and and lean is practice at Toyota, is pioneer at Toyota, right? So the goal here is to identify, and after we identify the waste, we eliminate the waste from the system, right? So that's the goal. But of course, before we eliminate the waste, you have to identify the waste first, right? Sometimes it's difficult to identify that as waste. And if we do not know it is waste, then how can we eliminate it, right? So the whole module 6 is about, number one is to identify the waste, and number two is to come up with some methods to eliminate the waste. All right. So I would like to show you some example of what it means by waste, right? First, excess capacity. If we have a very large restaurant serving, it can serve 100 customers at the same time, right? But at most we only have 50 customers. So in a sense, we already have more than enough capacity. And that's a form of waste because we invest a lot of money in our restaurant to have 100 seats, but then only 50 seats are underused, right? So we are wasting our investment money. Excess inventory is another form of waste because excess inventory means that we're gonna hold on, we hoard some extra inventory without selling it or without using it. Then in a sense, we lock up our money in the extra inventory, right? So that's a form of waste right there. Overproduction is another form of waste. So if we have orders, 50 orders of cars, which means that we sell 50 cars, right? But then we produce 60 cars, then we overproduce by 10 cars. It takes a lot of time to sell those 10 cars, and in a sense, right, we hold on to the inventory, and then we lock up our money in those 10 cars, right? So that's not good. Poor communication is another form of waste. For example, if we send out an email, something like that, with the wrong information, right, or something not clear, then you have to resend another email to explain what is going on. People shoot the emails back to ask for clarification, for confirmation, right? Then it is a waste of time for everybody. So that's another form of waste, or the source of waste, right? Long distance is another source that will lead to the waste. So, for example, just imagine you might have visited the Ontario Mills Mall, right? Just imagine it's a very long O shape like this. If there are no shortcuts between the two long legs of the O shape, then you will have to walk very long before you can reach the store that you want to go to, right? So that's why the management, before they build that mall, they already have to think about how to design it to cut down the walking distance, right? So they will make two shortcuts between the two legs of the O shape, so that the customer can move faster and reach their stores more quickly. And all the workers, all the merchandise can be kind of routed with a less distance, right? So long distance is another form of waste. We will have to walk for so long before we can reach what we want to reach, right? So we need to identify that as a waste and then try to cut it down. Clutter is another form of waste. Just imagine on my table right now, I have one cord for the laptop, one cord for the tablet, another cord for the cell phone, another cord for the headset, things like that. I have a lot of cords on my table, right? So if I need to put something on my table, I have to move things around. It takes time, right, to move things. So that's a form of waste. Of course, I want to do away with the clutter, but that means that I have to buy a new laptop. I'm sorry, a new device, or several new device that can be wirelessly charged, right? right? To take away the clutter. Or in a car factory, if we have a lot of cords on the floor like this, somebody might trip, we might have an accident, not to mention we might damage some of the cars, right, during the production process, just because of the clutter. Then the clutter are not good at all, right? The clutters are the source, is another source of waste. Excess energy use is another form of waste. So that's why at Walmart in the early morning, they only do half light in the stores, right? Because at that time there were not many customers around, uh, and some of the stores they even use the daylight through the glass ceiling, so they can cut down the energy use, right? The saving is huge because remember Walmart is the biggest retailers in the world, so they use a lot of energy, and if they can cut down some energy, then is huge already, right? Long wait is another form of waste because, for example, if you if your process has a small capacity, because customers have to wait for so long, they will walk away. They will buy from another seller, right? And that's why at Amazon they try to cut down the wait time. They do the Prime program so that they have a plan on how to cut down the time, right? And they are very good at that. That's why people come back to Amazon and buy again and again. Obsolescence is another form of waste. We carry some electronic devices, like a flat TV panel or a tablet or cell phone. They stay there for 1 year, right? Then the next year you have to mark it down before you can sell it. So that's a form of waste right there, right? So it means that we should not carry too much, right? If we carry too much, we will have the leftover, and then a lot of leftover, and then we have to lose money before we can sell it. Too early is another form of waste. If you go to a meeting, the physical meeting rooms, right? Too early, then you just stay there by yourself without your computer. You don't have the chance to do anything. Then we waste our time, right? Unproductive meetings is another form of waste. Unproductive meetings means what? After like several hours of talking, discussion, argument, then people walk away without any specific solution, right? Then that's unproductive. So that's why I think at Microsoft, they put out an initiative where they try to limit the number of meetings per week. The good effect of that is the following. If people know that they only have this number of meetings, then they have to get more prepared before they go to the meeting. They have to do research, they have to do homework on the problems at hand, think about the possible solution. And then when they meet up, right, they will quickly come up with a solution, and then that will be a productive meeting, right? Misrouting job is another form of waste. Let me tell you two stories of my own experience about misrouting jobs. I bought a shirt at Amazon.com, and it said it was delivered, but I could not find it, right? So after 5 or 7 days, my neighbor brought the shirt over. Turns out that the shirt was dropped in the wrong porch. It is a fence porch like this. There's no way for it takes more time for the neighbor to recognize that it is not belonging to them, right? So I'm not happy with that transaction. I might complain, and then the sellers might have to compensate me in some way, right? Then that's a form of waste. Or in the second incident, I got a package. Turns out it is not mine. It is for somebody's several blocks away. So I have to literally drive my car and drop off the package for Amazon, right? Think about it that way. If I'm busy, I will send it back to the UPS. The UPS will send back to the fulfillment center. And then from the fulfillment center, they resend the package to the person several blocks away, right? you think how costly it is, right? So you know what? We have a long list of waste here, but it's only some examples. In the reality, waste happens and exists in many forms. Sometimes it's quite delicate to realize that it is a waste, right? So, so we have to learn how to identify the waste effectively. Um, and for that, we only focus on two perspectives to identify the waste. Otherwise, we will get lost, right? So we always treat our company as a process. Then, in the first perspective, we try to look at the waste of time at a resource. Right, that's one perspective. The second perspective is we look at the waste of time of a flow unit. We track a flow unit from the beginning to the end and see when it is productive, when it is not productive. Okay, so that's an overview. I would like to reorganize it in the class notes so that we know where we are. All right, so today we move on to module 6 about lean operation. Then, of course, what is lean first? All right. It means that we have to identify and eliminate waste from our process, from our system, from our company. Okay, so I encourage you to review the example of Louis Vuitton. Louis Vuitton, right? They produce a handbag, right? Luxury handbags. So they drastically change the production process. And for that, they can significantly reduce the waste in the system, right? So that's a very clear example of lean operations right there. And of course, beside that, we just go through a list of some more example, right? Some examples of waste that we just discussed earlier. So it means that as a manager, right, if we know it is a waste, then we should find a way to cut it down. Otherwise, we are losing money, right? So this is, remember, that's module 6, slide 7. Because the waste exists in so many forms, so that's why to identify the waste. In our class, we only focus on two perspectives. The first perspective is the waste of time at a resource. Right? And the second perspective is the waste of time of a flow unit. So the reason why we have these two perspectives, because we always treat our company as a process like this. Right? Since the beginning of our class, we talk about a lot of things as a process. In our process, we have resources, workers, machinery, buildings, things like that, right? So that's one way. We look at the resources and ask ourselves when it is productive, when it is not, right? And then we also look at the flow units going through the process. We track one unit from the beginning to the end and see when it is productive, when it is not productive. If it is not productive, it is a waste. right? And we try to cut down the waste. So that's an overview about lean operations. And now let's do the first perspective. Let's look at the waste of time at the resource. So the next big topic is the following. We look at the waste of time of a resource. The resource here can be workers, right? Can be machines or equipment or other assets. So the time of a resource can be broken down into the following components. The first one is called the work time, right? And the second one is called the waste time. So it means that we talk about a worker, then we talk about the time that they work and the time that they do not work, right? For example. So we can break it down into two big categories: work time and waste time. And in the work time, we can break it down further to be the value at a time and non-value at a time. What does that mean by value at a time? For example, when we cut a part, we cut a part and then that part will go into the car. Then the customer will see it. They will value it. They will appreciate it at the end, right? So that cutting activity right there is a value-added activity. So we say that it is as a value-added time because that time will produce something that will be valued by the customers, right? Then we call that as a value-added time or the value-added activity. The non-value-added time is the following. They are necessary. The activities are necessary, but they will not be valued by the customer. For example, before we weld two parts together, we have to set the two parts to be close to each other at the right angle, at the right spot, things like that, right? And then we do the welding. The welding itself is the value-added activity because later on the customer buy the products, then they appreciate the good welding finish, right? And if it is a broken welding, then of course the customer will not be happy with it. So the welding activity is a value-added activity. But how we set up the weld before we weld it, right, is not the customer concern. They do not pay attention to that. They only want to buy the final products. They don't need to know. They don't want to know how we set it up, right? But it is necessary. That's why we call that setup as non-value-added, and they are work, right? But in terms of waste, then we have the following. Either we have the idle time. We hire a worker, but at that time the worker doesn't work, and definitely that's a waste of time right there. Or it is a wasted work, right? The worker actually works, but then they fail it in some way, and then they have to redo it again. They have to redo it, or they have to attempt it one more time or several more times, right? Then even though they work, but those work activities are wasted, right? So the waste time can either be the idle time where the workers or the machine they don't do anything, or even if they do something, they fail, right? In terms of the quality, then we also classify that as a waste. Right, so that's an overview of the waste of time of a resource. So now to really understand it, let me go through one example with you. Let me show you the example in the slide. It's on slide 19. Let me share that. A piece of equipment is available 24 hours a day, like a machine, right? On a typical day, by the way, we are looking at the waste of time at the resource. The resource here is a machine. On a typical day, the equipment produces 10 units. Each of unit takes about 60 minutes on the machine, 40 minutes of which is processing time, and 20 minutes of which is a setup time. About half of the units need to be reworked, right? In which case, the setup time and the processing time have to be repeated. The equipment is idle in the remaining time, right? So they try to give us the information here. What is a value at a time? What is a non-value at a time? What is a waste time? And what is a overall equipment effectiveness, right? I hope you recall this OEE when you do it on Connect. Okay, so let me work on this with you. I wish I had more time, but we only have 10 minutes remaining, so I will need to go through it quick enough. Okay, so this is a example of the waste of time of a resource. Right, we're already in module 6. The big topic is the waste of time of a resource. Earlier we got the overview, and now we look at the example. This is module 6, slide 19. So we have a machine that is available for 24 hours a day. So we call that available time as total available time, or TAT, right? Total available time. It is available for 24 hours, but we need to convert it to minutes. So we would do 60 times 24, and we have 1,440 minutes. And then our task is the following. We need to break this total available time into the value at a time, then the non-value at a time, and then the waste time. Right. So that's a task that we have to do. Before we go further, let me go back to one piece of information that we have here. The machine will have to do 10 jobs a day, out of which 5 jobs are good, meaning that the machine does it right in the first attempt. But beside those 5 good jobs, there are 5 rework jobs, meaning that we did it the first time, but we failed, and then we have to do it the second time, right? So, and here's the thing. Now we can break down each of the 3 categories here in further details. The value at a time is the following. First of all, it is a processing time. of the five five good jobs. Processing, for example, we cut a piece, we drill a hole, we put the two parts together, we weld the two parts together, right? It is processing time. Or we put the screw or the bolt to secure the door on the car, right? So that's a processing time. And then it is value added because the customer will value our activity, right? So that's a processing time of five good jobs. The calculation itself is very easy, right? It takes 40 minutes to process a job, and there are five jobs here. So this this entry is 200 minutes. Okay, and we have the processing time of the five rework jobs. I would like to ask the whole class, when we talk about the processing time of five rework jobs here in the value added time here, do we count the first attempt or the second attempt? Please feel free to type your answer in the chat window. Do we count that in the first or in the second attempt? I see some of your answer here. Right. Remember, we talk about the rework job. Okay, so I have another answer from Micah, from Harlan and Sylvia and Micah. Anybody else? Here we talk about the processing time of five rework jobs, right? So rework jobs means what? It means that we fail in the first attempt. That's why we have to redo it, rework on it, right? So that's why for the value at a time, we should not count the first attempt because the first attempt is a failure. Then it is a waste. We should not count it here, right? So let me clarify here. This is a processing time of five rework jobs in the second attempt. It's a little bit confusing. This is the first time that possibly we have to think about it like this, right? Normally, rework is rework. It's not a waste of time at all, right? But now we are doing lean operations. We are more conscious about this. The calculation itself is very easy. It takes 40 minutes per job, and then there are five jobs here. So the total, the processing time of these five rework jobs is 200 minutes. Okay. So in total, the value at a time is 200 plus 200. Then we have 400 minutes. Everything here is in minutes, so I just omit the units. Okay, so that's a value at a time. I hope now you see that right. What is the non-value at a time? So we break it down into the the setup time of five good jobs, right? We have to set it up first before we can could either weld it or cut it or do some other value-added activities. So it is necessary, but the setup is not valued by the customer. So it is the non-value-added. It takes 20 minutes per job. And then we have five jobs, so in total we have 100 minutes right here. And then we also have to talk about the setup time of the five rework jobs. Right. Is that the first attempt or the second attempt? What should we count here? I hope now everybody sees that we should not count the first attempt here, right? That's right. That's right. Because the first attempt is a failure. The worker set it up and then cut it, and then he or she finds out that it is a wrong cut. So the setup is wasted, right? The cut itself is wasted, but the setup is also wasted. So we should not count the first attempt here. It should be the second attempt. Right. So, and then we know that it takes 20 minutes per job. We have 5 jobs. So we multiply them, we have 100 minutes. So the non-value added time here, if you just add 100 with another 100, then we have 200. Right. The calculation itself is not that difficult. It's just basic calculation. But the concept here are the more tricky things. All right, so we're done with the value at a time, the non-value at a time. Then, you know what, even before we know the details about the waste time, we can calculate the total waste time, right? Because we already know the total available time right here. We know that. We just subtract, then we have the total waste time. So for this, we take 1440 minus 400, the minus another 200, then we have 840 minutes, right? Waste time in total. So what are the components in the waste time? The first one is, that's the processing time of the 5 rework jobs, right? Processing time sounds like value added, but because it is a failure, so we should classify them as a waste time. So that's why we write here as a first attempt, right? The calculation itself is easy. We just take, I wish I had more space here. So we would take 40 minutes per job times 5, then we have 200 minutes, right? And then we have the setup time of the 5 rework jobs. And remember, that also is at the first attempt. Right? If we cut it wrong, then the setup of that cut is wasted. So we list it here. So the calculation is also easy. We take 20 times 5, and we have 100 minutes, right? All right, and finally, the final item here is idle time. I'm sorry, my notes is quite cramped right now. And so the idle time is what? It is the remaining time, right? I'll do it very quick. The idle time is 840. So the idle time is 40 minus 200 minus 100. We have 540, right? Minutes of idle time. So at the end, the very final calculation is OEE, right? Is value at a time divided by TAT equals 400 divided by 1440. Then we have 27.8%. Okay. So with that, I would like to end the class here. This review example that will show up as question 24 in our homework 3. So have a great weekend. Have a great rest of your day, and then I'd like to see you next Monday. All right. I'd like to thank you all.
Professor?
Yes.
I have a question for the project.
Yes.
Is the the first part of the project, is it only part 1 that is due?
No, for the checkpoint, part 1, 2, 3 are due.
1, 2, and 3?
Parts 1, 2, 3, yeah,
Okay, all right, thank you.
sure.